It's absolutely mind-blowing what AI can do these days, from writing your code to creating stunning art. But behind all that magic of models like Gemini, there's this massive, hidden physical world of processors and power. Today, we're going to pull back the curtain on the secret ingredient that keeps this whole AI revolution from, well, literally melting down.
And no, that's not a metaphor. I mean that literally. Every single tiny calculation an AI makes generates heat. And as these models get exponentially more powerful, they create a thermal problem on a scale we have just never seen before. So how in the world do you cool down the future?
Just look at this timeline. It really tells the whole story. From BERT back in 2018 to Gemini 2.0 today, the amount of computing power needed has just exploded. We're not talking about a gentle curve here. This is a vertical climb, like a rocket launch. And all of that compute, all that electricity, it turns into an incredible amount of heat.
And that brings us right to the core of the issue. This massive growth in computation creates a very real, very hot physical consequence. It's like an unseen heat wave that's happening inside data centers all over the world.
The funny thing is, cooling powerful computers isn't a new problem at all. If you go way back to the 60s, the old mainframe computers were liquid-cooled. Then, chips got so efficient that, for decades, just blowing air over them was good enough. But since the 2000s, chip power started to skyrocket again, and now the AI boom has brought us full circle. We're back to needing liquid, but this time on a scale nobody could have imagined.
So how did one of the biggest players in the AI game, Google, decide to tackle this problem head-on? Well, this wasn't some overnight fix. It was a decade-long engineering quest.
Their journey actually started way back in 2014, with some really bold experiments and, just as importantly, a lot of failures. By 2018, they had a working product for their specialized AI chips, the Tensor Processing Units, or TPUs. And for the last 5 years or so, they've been obsessed with just one thing: figuring out how to scale it to an almost unbelievable size.
Okay, so what do they actually build? Let's go inside the machine, get under the hood, and break down exactly how this tech works piece by piece.
It all starts right here, with this little component called a cold plate. The best way to think of it is like a tiny, super high-tech radiator that sits right on top of the AI chip. It's a solid copper block, but inside it is filled with these microscopic channels. Its one and only job is to suck the heat directly out of the silicone by running liquid through it. This little piece is the critical point of contact. It's where the heat from the digital world physically meets the coolant.
Now, that cold plate is just one part of a much bigger system. At the center of it all is the Coolant Distribution Unit, the CDU. You can think of it as the heart of the entire system, pumping out cool liquid. From there, things called manifolds act like arteries, spreading that liquid out to every single server. The cold plates, as we saw, absorb the heat, and then the now hot liquid flows back to the CDU to get chilled down and start the whole cycle over again.
And you can really see how this technology evolved right here. The first version for their TPU-V3 chip was pretty straightforward. It ran coolant through the chips one after another, kind of like a single-file line. But the newer system for TPU-V4 is so much smarter. It uses a parallel flow, which means every single chip gets fresh, cool liquid at the same temperature. And maybe most critically, it cools the bare die. That's the raw exposed silicon with no lid getting in the way. It's just a much more efficient way to pull that heat out.
And here's the heart itself, the CDU. Now the genius part is that it's not one single giant pump. It's actually a rack of 6 smaller modular units that are hot swappable. This whole design is about reliability and easy maintenance. If one unit fails, another one just takes over instantly. And because of the flexible hoses and quick disconnects, a technician can just pop one out and slide a new one in without shutting the whole system down. It's pretty smart. So this intense focus on reliability and this modular design, it allowed Google to do something pretty incredible: achieve absolutely massive scale without giving up performance or uptime.
Just take a look at this number. Let it sink in for a second. 99.999%. What on earth could possibly be that reliable? It's not your phone battery. It's not your Wi-Fi connection. Any ideas?
That number, that's the uptime of Google's entire liquid-cooled fleet since 2020. That's what engineers call 5 nines of reliability. And it's about as close to perfect as you can get.
It's achieved through just relentless design. That N+1 redundancy we just talked about, where there's always a backup ready to go, combined with super rigorous testing and constant monitoring, it makes the system almost fail-proof.
So how big is this fleet we're talking about? By 2024, the total deployed capacity of these liquid-cooled systems hit approximately 1 gigawatt. To put that into perspective, that is roughly the same output as a full-scale nuclear power plant, all dedicated to cooling AI chips. It's wild.
And was all that effort worth it? Oh yeah, the results are just staggering. When you compare it to the last generation that used air cooling, this liquid system let Google double the density of their chips, build supercomputers that are 4 times larger, and run the processors 30% faster. And maybe the most amazing part? All the pumps for this liquid use less than 5% of the power that massive, noisy fans would have needed.
So all of this makes one thing crystal clear. Liquid cooling isn't just a cool option anymore. For high-end AI, it's a fundamental necessity. And as we look to the future, the challenges are only getting bigger.
Yeah, looking ahead, the whole industry is facing some major hurdles. Chips are getting even more powerful, creating these intense hotspots. We're seeing new 3D chip designs that are way harder to cool. And the entire supply chain for all these specialized parts, it needs to grow up fast. All while these systems need to be deployed faster and more sustainably.
Now, to help solve this, Google is doing something pretty remarkable. They're taking all the lessons learned from their 5th-generation system, which is codenamed Project Deschutes, and they're sharing the specifications publicly. They're essentially creating an open standard so the entire industry can work together to build compatible and efficient systems to power this next wave of AI.
And that brings us to the fundamental question for the entire future of AI. We know its appetite for power is just going to keep growing. So the real race isn't just about building smarter algorithms, it's about building smarter, more powerful, and more sustainable ways to keep them cool. As AI continues to reshape our world, it's this unseen world of cooling engineering that will ultimately determine just how far and how fast it can really go.